we're going to do is continue on our coverage of the Taylor's theorem, and specifically our goal is to basically interpret Taylor's theorem a bit more. So to recall, I have just rewritten the statement of Taylor's theorem, namely that if f is n times differentiable over an interval where which contains c as well as the point x at which we are evaluating the approximation, then the evaluation of the function at x is equal to the n minus 1th order Taylor expansion of f around c plus an error term. This error term is also often called the remainder, okay, which we have denoted by Rn of x, and this error or remainder can be expressed basically as x minus c raised to n by n factorial times the nth derivative of f at some point y between x and c. Right? This was the characterization of the remainder that was provided by Taylor's theorem, which, if you recall, was proved by an n times application of Rolle's theorem. Okay, so let's first look at a simple corollary of this. Right, so if all the derivatives are bounded, so if all derivatives of f exist firstly on AB and are bounded in absolute value, by some constant c. C is probably unfortunate. Let's use some other notation. Let's say beta greater than 0. Then, in fact, it's easy to see that Rn of x will actually tend to 0 as n goes to infinity. Right? So if f is infinitely differentiable, okay, and if it also turns out that every derivative, the value of the derivative everywhere is in fact bounded above an absolute value by some constant beta. In other words, for any x, fn of x, absolute value of that is less than equal to beta, where beta is some positive constant. Okay, if it is indeed possible for for all higher derivatives of the function to be uniformly bounded above in this fashion, then it's a trivial observation to see that your remainder for any x will actually tend to 0 as n tends to infinity. Okay, in other words, as you include more and more, shall we say, terms in your Taylor expansion, as you take a higher and higher order Taylor expansion, the error or the remainder term will in fact tend to 0. Right? Why does this follow? Because the derivative fn of y is upper bounded by beta, and then all you have to argue is that as n tends to infinity, x minus c raised to n by n factorial must in fact tend to 0. Right? However, you should, so while this is in fact, an easy consequence of Taylor's theorem, you should note that the class of functions for which this holds is also very restrictive, right? You don't need it just to be infinitely differentiable, but you need every derivative to be uniformly bounded by some constant, right? Every derivative to be bounded everywhere by the same uniform constant. So you can imagine that only a restrictive set of functions would in fact satisfy this, right? And the reason why a very restricted class of functions is expected to satisfy this is because effectively we are saying that no matter how far x is from c, as you take a higher and higher order polynomial approximation of the function around c, it somehow becomes increasingly accurate around x, right? Irrespective of how far x is from c, right? Which you should expect is going to be, a tall ask. The function itself has to be special enough for that kind of property to hold, right? Because after all, the nth order Taylor expansion of f at c depends only at the behavior of the function at c, right? Or rather in a neighborhood of c, because all you're bothering with are the derivatives of the function at c. So that such local information of the function will still basically tell you something very useful about the function far away, should therefore say something very special about the function itself. Right? So it's not surprising that only for a very restrictive class of functions would the error just go to 0, irrespective of how far x is from c. Right? more typically, Taylor expansion is going to be useful for x itself being sufficiently close to c, right? And one way of basically stating and interpreting this is using the order notation, right? So which I'm going to introduce very quickly here. So notation. So we say that a function f of x is little o of g of x as x tends to 0. Okay, now because so at this point just take it like this: f of x is equal to little o of g of x as x tends to 0 if the following is true. If limit as x tends to 0 of f of x by g of x is in fact equal to 0, right? So if f of x is little o of g of x, that means that f becomes basically negligible compared to g when x approaches 0. So f is negligible compared to g as we approach 0. Okay, as an application of this, and the connection to Taylor's theorem will become apparent shortly, but at this point just take this as a definition, right? F of x by definition will be called little o of g of x if f is asymptotically negligible to g, where in this case the asymptote is as x tends to 0. Okay, so note that the function x is little o of 1, right? This makes sense because the function x does indeed become negligible compared to 1 as you approach 0, right? Similarly, x square is little o of x, right? X squared, again, it's a trivial application of the definition to verify that this is true, but again, intuitively you should expect that x square does become negligible compared to x as one approaches the origin, right? Similarly, x cube is in fact little o of x square, right? And so on. Okay, so now using this little o notation, we are going to interpret essentially the error or the remainder associated with Taylor's theorem. So back to Taylor's theorem. Now to perform this interpretation, let me just take C to be 0, right, without loss of generality, right? So I'm going to consider the Taylor expansion around 0, okay, just to make the representation cleaner. And I'm also going to assume that f is sufficiently many times differentiable on, well, some interval around 0. For simplicity, I'm just going to take that to be the interval from -1 to 1. Okay, this is interpretation. I'm not this is the goal here. My goal is not to be particularly formal, but to give you a good interpretation, a way of thinking about Taylor's theorem. Okay, making this precise is not particularly difficult. So for simplicity, we will take C to be 0, and just so that I don't have to keep saying that f is so many times differentiable, let's pretend that f is sufficiently many times differentiable in the closed interval from -1 to 1. Right? Then the claim is as follows. Then f of x is equal to, now I'm going to write the nth order Taylor expansion just for notational simplicity. So that's fk of c plus right, plus a remainder term, which you should be able to realize is in fact little o of x raised to n. Okay, so remember that f of x where I've written the nth order Taylor expansion, the last term of the Taylor expansion is in fact of the order of x raised to n, right? Specifically, it has an x minus c raised to n factor there. The remainder term I'm claiming is now little o of x raised to n. Now, why is that? Well, the remainder term is in fact equal to fn, or at some point y, sorry, fn plus 1 at some point y, right, between x and 0 times x raised to n plus 1 by n plus 1 factorial, right? Now the thing to note is that this fn plus 1 of y is in fact bounded on the interval from -1 to 1. Why is that? Well, if I assume that f is sufficiently many times differentiable, in particular if f is n plus 2 times differentiable, then fn plus 1 is a continuous function on the closed interval from -1 to 1, and so therefore it must be bounded, right? You must be able to bound it, bounded uniformly over the interval from -1 to 1. Therefore, there exists some constant such that fn plus 1 of y is in fact upper bounded by that constant, which doesn't depend on x, right? And then you see that the remainder term essentially becomes can be bounded certainly by some constant times x raised to n plus 1, which makes it little o of x raised to n. Okay, so the way to now think about this is that the Taylor, if you take the nth order Taylor expansion, that is basically going to incur an error that is little o of x raised to n. In other words, as x is sufficiently close to 0, the error is of the form little o of x raised to n, right? The error is, is asymptotically negligible as x tends to 0 to x raised to n, which is in fact the last term of the Taylor expansion. Okay, so this is the way to think about this, and specifically, yeah, so I'll just write this first. So for f close to the origin, the nth order Taylor expansion yields an error that is little o of x raised to n. And it also tells you therefore how the error in some sense becomes smaller, or at least decays to 0 faster as you take higher and higher order Taylor expansion, right? So if you take the first order Taylor expansion, then your error is little o of x. The second order Taylor expansion, the error is little o of x square, right? And little o of x square is in fact asymptotically negligible as compared, it's basically decays to 0 faster than little o of x, right? So as you take more and more terms into your Taylor expansion, it gives you an informal way of understanding that the error associated with the Taylor expansion decays that much faster as x approaches 0. Okay, so in this sense, the error shrinks faster with more and more terms in the Taylor expansion. Right? This is only for interpretation, right? This is the way you can think about the error associated with the Taylor expansion. Okay, so there's one final kind of comment I want to make, and that is in fact a connection between Taylor's theorem and L'Hopital's rule, which we talked about just before. Okay. Okay, the point I'm trying to make here is that it is just useful to understand that oftentimes an application of L'Hopital's rule boils down to an application of Taylor expansion. Okay, so let me interpret that in the language that we have just described, right? So let's take the simplest example that we used before, which is limit x tends to 0 of, well, sine x by x. Okay, now the sinusoidal function is of course any number of times differentiable everywhere. So I'm going to just basically consider the first order Taylor expansion of sine around 0. Now sine 0 is 0, right? So it's going to be 0 plus, well, I leave it for you to verify that the first order approximation is in fact going to be x. So you're basically supposed to look at the derivative of the sine at 0 into x, right? That is in fact going to be the first order approximation plus little o of x upon x. Okay, and it's easy to see that x plus little o of x by x is in fact equal to 1. So yeah, I should write this more carefully. Limit x tends to 0 of this, which is going to be equal to 1, right? Because something that is little o of x, by definition, when you divide it by x, will go off to 0, right? So therefore, when you say that sin x by x has a limit of 1, what you're essentially applying is a first order Taylor expansion of the sinusoidal function around 0. Okay. Similarly, suppose I want to look at x tends to 0 of, let's say, sin x minus x upon x square. Okay, I want to understand this limit. Well, I now continue my Taylor expansion of sin x. Now, if you apply this, the definition of Taylor's expansion, but run it all the way up to the third term, you will realize that the expansion for sin x looks like this. It will be x minus x cubed by 3 factorial, right? Plus, of course, little o of x raised to 3. Right? So if I stop at the third order Taylor expansion, the error is going to be little o of x raised to 3. Alright. So when you do that, well, you realize that if you look at sin x minus x upon x square, this is in fact going to be equal to, well, minus x cube by 3 factorial plus little o of x cube upon x square, which of course tends to 0 as x tends to 0, right? Because this is little o of x cube. Even if you were to divide by x cube, that second term will go off to 0, and then x cube by x square is of course x, or x times some constant, which also goes to 0 as x tends to 0, right? So therefore, again, this limit boils down to taking a sufficiently high well, Taylor approximation of this, right? And it's not surprising because if we were to apply L'Hopital's rule, you would have to apply L'Hopital's rule a couple of times, right, to be able to characterize this limit. So therefore, you have to take a sufficiently higher order Taylor expansion as well. In fact, even if you just used a second order Taylor expansion, this would have been sufficient. I just wrote the third order Taylor expansion, to illustrate what the expansion of sin x indeed looks like. Similarly, suppose one last example. Suppose you wanted to look as the limit as x tends to 0 of, let's say, log 1 plus x upon x, right? This also can now be interpreted as just a Taylor expansion. Now in this case, we are going to take the Taylor expansion of the function log of 1 plus x around x is equal to 0. Okay, so the 0th order term is just going to be 0, because when you substitute 0 to this function, the value is 0, right? So again, I leave it to you to work out that in fact the expansion looks like this: x minus x squared by 2 plus x cubed by 3, and so on, right? There are you can keep adding plus, minus, let's say, x raised to 4 by 4, and so on. And wherever you stop, the error is going to be little o of the last term that you have written. So it's going to be little o of x raised to 4, right? So therefore, this is also, of course, trivially, I mean, I wrote more terms of the expansion just for illustration, but for this example, all that matters is that this is therefore x plus little o of x, right? So therefore, we would see that log of 1 plus x upon x is in fact x plus little o of x by x, which of course tends to 1 as x tends to 0, right? So this is just to illustrate that oftentimes when one is applying L'Hopital's rule, what one is really doing is, in the examples that I've given here, we have only taken the Taylor expansion of the numerator. If you have understood what is happening here, you should be able to convince yourself that oftentimes one is basically just taking a Taylor expansion of the numerator, a Taylor expansion of the denominator, and then figuring out what is the limit of this ratio by basically looking at that ratio of Taylor expansions. Okay, so that is all I had to say about interpretations of Taylor's theorem. So we'll stop here, and this brings us to the end of the chapter on the derivative.